everybody. Welcome to our second chapter, which is the symmetric encryption and message confidentiality. When we said symmetric encryption, we can also say it is a kind of conventional encryption, or sometimes we call it as a secret key or single key encryption also can be used. Anyway, in this chapter, we begin with the symmetric encryption. Then we look at the three important block encryption algorithm like DES, triple DES, and also AES. And finally, we look at the random and pseudo-random number generation. For next chapter, inshallah, we will go through the symmetric stream encryption and also the important topic of the block cipher modes of operation. All right, symmetric encryption scheme, in fact, has 5 ingredients. If you look at the figure 2.1, the first one is the plain text input. So this is the original message or data that is fed into the algorithm as input. So this one we will give it to the algorithm. Let's say here we have the, for example, AES. So the encryption algorithm performs the various substitution and transformations on the plain text itself. All right. It uses the secret key, right? So the secret key, in fact, is the another input to the algorithm. So the exact substitution and transformations performed by the algorithm, and it depends on the key itself. So how basically you have defined the key. The next ingredient is the ciphertext, right? So this is the scramble message. We call it scramble message. This is produced as an output. It depends on the plain text and the secret key. All right. So both of these will be used by the encryption algorithm, and we will get the ciphertext out of the algorithm. In fact, for a given message, two different keys will produce two different ciphertexts. So different key, different ciphertext. And then we have the decryption algorithm. So when we want to decrypt it at the receiver, so the encryption will be done at the sender side and the encryption will be done at the receiver side. This is essentially the encryption algorithm run in reverse. We call it decryption. And it basically takes the ciphertext and the same secret key. The key important issue here is the same secret key will be used to produce the original plain text. All right. So the key here for encryption and decryption is same. That's why we call it symmetric encryption. Right. There are two requirements for secure use of symmetric encryption. So we need a strong encryption algorithm. At a minimum, we would like the algorithm to be such that an opponent or attacker who knows the algorithm and has access to one or more ciphertexts would be unable to decipher the ciphertext or get out the plain text. So these requirements is usually stated in a stronger form. The opponent should be unable to decrypt the ciphertext or to discover the key even the opponent or attacker is possession of a number of ciphertexts together with the plain text. Even though he has access to such things, he should be unable to decipher or decipher the ciphertext, right? The second one, the sender and receiver must have obtained the copies of the secret key in a secure and fashion way. Okay, if someone can discover the key and knows the algorithm, all communication using this key is readable. So let's say if an attacker is a man in the middle attack and can capture all the packet, all the communications between the two nodes on the net, so definitely he can capture the key, he can also discover the key, and also if he has the algorithm, so everything can be readable to him. So it is important to note that the security of symmetric encryption depends on the secrecy of the key. That is very important, not the secrecy of algorithm, because algorithm, it's known to everybody. So that is assumed that it is impractical to decrypt a message on the basis of the ciphertext plus knowledge of the encryption decryption algorithm. It should be impractical. All right. In other words, we do not need to keep the algorithm secret. We need to keep only the key secret. That key secret is the key element, I can say here. All right. So this feature of symmetric encryption is what makes it feasible for widespread use. The fact that the algorithm need not be kept secure means that the manufacturer can develop the low-cost, cheap implementation of data encryption algorithm and give it to everybody, available to everybody. So shouldn't be any problem. Okay, that is a requirement. The cryptographic systems are generically classified along three independent dimensions. Okay, the type of operation used for transforming the plain text to ciphertext, the number of keys used, and the way in which the plain text is processed. Okay, that is the three classification. Okay, the first one is substitution, the second one is transposition, and the third one is product the systems. So substitution, each element in the plain text is mapped into another element. Transposition is element in the plain text are rearranged. Later we will see the example how basically the word will be rearranged. It's simply rearranged, but you should know the algorithm. Later when you want to decrypt, you have to apply this algorithm in reverse. Right? And the fundamental requirement is that no information be lost. You must be careful of that. So the product systems involve the multiple stages of substitution and transposition, not only one time, maybe 16 times, maybe more than that, less than that, depends on the algorithm. Okay. So the second one is the number of keys used, referred to as symmetric or single key. Sometimes we call it secret key or conventional encryption. If both sender and receiver use the same key, we call it symmetric. Otherwise, if different key, we call it asymmetric. All right. So we have two key or sometimes we call it public key encryption. We will see why we call it public key. If the sender and receiver each use a different key, let's say I want to encrypt the message, I use a key, and the receiver when want to decrypt the message will use another key to decrypt it. All right, so that we call it asymmetric. The way in which the plain text is processed, we have the block cipher process that input one block of element at a time and producing an output block for each input block. Okay, so we have a block cipher, and the second one is a stream cipher. So the stream cipher processes the input element continuously, producing output one element at a time as it goes along. Okay, so it receives and then it generates the stream cipher. It's not block by block, right? It's a continuously producing the output. Okay, that is a kind of cryptography. So let's look at the type of the attack. The process of attempting to discover the plain text or key, we call it cryptanalysis. Okay, we call it cryptanalysis. The strategy used by the cryptanalyst analyst depends on the nature of the encryption scheme. Okay, if you look at the table 2.1, It summarizes the various type of cryptanalytic attacks based on the amount of information known to the cryptanalyst. Okay. The most difficult problem is presented when all that is available is the ciphertext only. All right. In some cases, not even the encryption algorithm is known, but in general, we can assume that the opponent does know the algorithm used for encryption. So one possible attack under these circumstances is the brute force attack that we will see in a little bit more detail later. Okay. So what is the meaning of brute force attack? Which is trying, if I can say, explain it in a short messages, is kind of trying all possible keys. Let's say the combination, let's say you will try A, then B, then C, then D, E, F, and so on, and then you start with, A, B, A, C, A, D, and so basically you are trying all possible keys. So the ciphertext only attack is the easiest to defend because the opponent has the least amount of information to work with it. So the closely related to the known plaintext attack, the second one, is what might be referred to as a probable word attack. If the opponent is working with the encryption of some general prose message, he or she may have little knowledge of what is the message. However, if the opponent is after some very specific information, then part of the message may be known. For example, if an entire accounting file is being transmitted, the opponent may know the placement of certain key in the header of the file. Because when you want to send the data, basically the key also must be included. So later we will see we will look at this kind of what do you call it, the algorithm, how basically the keys will be transmitted. So in some cases, the attacker know the place of the key, so they can get the key, and also they have the message, they can decrypt, right? If the analyst is able somehow to get the source system or insert into the system a message chosen by the analyst, then a chosen plaintext attack is possible. Okay, but in general, if the analyst is able to choose the message to encrypt, so the analyst may deliberately pick patterns that can be expected to relieve the structure of the key. So this table 2.1 lists two other type of attack. We call it the chosen ciphertext and chosen text. Okay, the last two one. These are less commonly employed. So that's why you can see some more information. Encryption algorithm, ciphertext to be decoded, and so on and so forth. Okay, but they will be useless. Only relatively weak algorithm fail to withstand a ciphertext only attack. Generally, encryption algorithm is designed to withstand a known plaintext attack that we already explained. An encryption scheme is computationally secure. Okay, if the ciphertext generated by the scheme meets one or both of the following criteria, then I can say the encryption scheme is secure. The cost of breaking the cipher exceeded the value of the encrypted information. Okay, so sometimes it's not valuable. Some information you want to spend around 10 days to decipher or to decrypt the message as an attacker, but there is no such value for that information. Why should I do that? And the second one is the time required to break the ciphertext exceeded the useful lifetime of the information. For example, when you want to transfer money using the online banking, you will receive the code, right? That CC or some kind of, the code or the secret key, I can say here, maybe is useful, or the lifetime is, let's say, is for 60 seconds. Okay, but if the attacker need at least 5 minutes, for example, to get this information out, so it's not useful at all. It's useless. because the lifetime of the message of the information is only 60 seconds, for example. But the attacker need at least 5 minutes. So basically is not feasible. Okay. As I said, we discussed about the brute force attack. Unfortunately, it is very difficult to estimate the amount of the effort required to cryptanalysis the ciphertext successfully. We cannot say exactly. Assuming there are no inherent mathematical weaknesses in algorithm, the brute force attack approach is indicated. A brute force attack involves trying every possible key until we find out we obtain the plain text out of the ciphertext. On average, of course, half of all possible keys must be tried. Let's say you want to try 3 words, for example, at least half of that need to